Okay, welcome everyone to today's Got Enough seminar. Today we're really happy to have Anatoly Dymarsky joining us from University of Kentucky or Moscow. Tolya has worked on many aspects of conformal field theory in various dimensions. He's also an expert on eigenstate thermalization. And more recently, he's focused specifically on 2D conformal field theories, as well as aspects of quantum information theory in this context. And I think this talk will be related to that. So the title for today's talk is Quantum Codes, Conformal Field Theory, and Holography. Thanks for joining us, Tolya. You can go ahead.
Luca, thank you for inviting me for the opportunity to speak. I'm excited to give a talk about some recent and ongoing work connecting conformal field theories with quantum. So you will see, well, this is and we understood some bits of it, but as you will see, there is a lot of ongoing activity and there are a lot of open questions which are completely unclear. So this is very much work in progress. The plan of the talk will be the following: introduction and review what class codes are and how to connect them to lattices and field theories. And then the main talk would consist of two logical. First part would be discussing, would be using codes to study properties of specific special conformal field theories with some extremal properties. So that's can be mapped to conformal theories. Of course, not all mapped back to codes, but only some special ones. Very special codes, we can have conformal field theories with some extremal properties, and sometimes would be special from the modular bootstrap point of view. So that's sort of, after we explore that, there will be another part where we will actually study ensembles of codes. That's a really recent thought that to have holographic correspondence on a boundary side, you need to have not one. We don't have many examples of those holographic ensembles, and we do not really have ensembles. And saying that codes provide a new playground to study ensembles of conformal theories in the holographic setting. So let me do the fair part. Of course, I welcome your questions throughout my talk, especially because this is a Zoom talk and I cannot really see you, and I cannot see how well I can get my message across. So I would appreciate your comments and feedback during the. I will start with the technical part. Classical binary codes. What is a classical linear binary code? It's essentially, we can define them mathematically in a very simple way. Mathematically, we can say that this is just a k-dimensional vector space embedded into n-dimensional space. So this is some vector space embedded in another high vector space. But instead of working over the field of real numbers or over the field of complex numbers, as we usually do in physics, in this particular setting, we are working over the field of two elements, 0 and 1. Here, I'm committing some crime and abuse of notations. The field consisting of two elements, 0 and 1, is denoted F2 in mathematics. I denoted it as Z2 for simplicity. This is just 0 and 1. Now, this definition is complete and it's good, but it doesn't probably give you any intuition unless you work with unless you work with finite fields before. So let me start again and explain what linear code is. Linear code is basically a collection of code words. A code word is a binary string of zeros and ones. So basically you have n elements and each element is 0 and 1. So this binary string is a code word. You have k strings. These are your, if you wish, this is your basis in the linear space. And after that, you start adding this basis code words together in all possible 2 to the k combinations, and you do all the algebra mod 2. So if you add 2 ones together, 1 plus 1 is equal to 0. 1 plus 0 is equal to 1, and 0 plus 1 is equal to 1. Okay, so you do algebra mod 1. So starting from k basis code words, you have 2 to the k all possible code words, and this they obviously form a linear space, and this is your classical code. Now, there is a nice geometric way. Each binary string, like, think of it as a coordinate of a point in n-dimensional space. Obviously, here on the slide, I have shown a cube in 3 dimensions. 1, 1, 1. Obviously, this string, this point, right? So you can start labeling vertices on a unit cube. In principle, can you hear me?
Yeah, we can hear you. It cuts off from time to time, but as long as you speak slowly enough, I think we can.
Okay, please interrupt me if there is no connection, okay?
Yeah.
Thanks. So you code words, you can start labeling vertices on a unit cube. So basically, a classical code is a collection of highlighted vertices on a unit cube. The fact that this is a linear code actually means that you can interpret this, the highlighted vertices as vectors and start doing linear algebra with those vectors. Now, since this is a linear space, there is always a trivial code word consisting of all zeros. That's the origin. So let's consider an example. Let's consider an example of a very simple code, which would basically consist of 2 code words, 0, 0, 0, and 1, 1, 1. So these are 2 highlighted vertices on a unit cube. Now, an important characteristic of a code is how good it is to encode and decode and protect. I will not go into details of how you are supposed to encode information and protect information, but geometrically, a good code is a code which maintains very large distance between code words, between highlighted points. Distance, d, it's called Hamming distance, is simply the distance an ant need to walk through an ant. Need to walk along edges from one point to another. In this case, this is the distance, and in this case, it is equal to 3. Okay, so this particular code, which consists of 2 code words, has Hamming distance 3. It is denoted 3, this is n, 1, this is k, and 3, this is d. Okay, standard notations. Now, what is an art of having a good code? What is an art of designing a good code? Basically, you take a unit cube in n-dimensional space, and you try to pick as many vertices as you can in that cube. You have, in an n-dimensional cube, you have 2 to the n vertices. So you try as many of those vertices as you can, maintaining a large minimal distance between any 2 points. The distance between as large as possible. If you try to pick more and more points, at some point those points close to each other, so your Hamming distance will become small. So this is a tension. The art of designing a good code is to be able to pick as many points as possible while maintaining minimal distance as large as possible. How to do it is an unsolved mathematical problem. People don't know for dimension n, which is sufficiently large, how good of a code you can have. So that's surprisingly, the situation is exactly like that. If I tell you that you have number n, which is divisible by 2, and k is equal n over 2, and n is sufficiently large, people don't know what largest minimal distance between any 2 points you can achieve. That's simply not known. And asymptotically, people don't know how to do it. Okay, so this is a classical code. So
what does good mean? You say you need a large Hamming distance for it to be good, but it's good for what?
The better code is, the larger D is. So the best code has largest D. Why?
So the definition of good is large D?
Yes, yes.
Okay.
I should spend 1 minute explaining why people care about D, because if you have an error or noise in your channel and you try to send through the channel this message, which is 111, it will get corrupted. So it means that one of these ones will become 0. And it means that this point will move somewhere, but it will move along the edges and a little bit. To be able to return it to the original point where it was, this point should not be able to migrate to new blue. So if and this point only moved a little bit, you should be able to the original place. So that's basically error correcting, classical error correcting code. Good. So let me give you basics of code theory. Since codes form a vector space, you can define a dual code, which is simple. For us, this will be an important notion, a dual code. Second thing, if you have a code word, each code word by the distance between that code word, this is called Hamming weight, and by modulus, or in terms of algebra, this is simply c squared, simply the number of ones in this binary string. The spectrum of the code is the Hamming length, or the length of the vector, the length of every single of your code. So the spectrum of the code is basically 2 to the k numbers. It is convenient to this information in terms of this homogeneous polynomial. This polynomial is uniquely specified by the spectrum of the code. That's the only information which is in this polynomial. But this polynomial is a convenient vehicle. For example, if your code is self-dual, if it is as a vector space self-dual to itself. Something like that would not be possible over the field or over the field of complex numbers, over binary field. So if your code is self-dual, it means the enumerator polynomial satisfies certain algebraic identity, which is called Mark-Williams identity. And basically, to prove it, you need to do a discrete Fourier transform. And then another trivial identity, well, Mark-Williams identity is not trivial. Another identity is trivial. If you say that code is double even, which means that the length of every single vector is divisible by 4, then it means that y in this polynomial will be taken to the power divisible by 4, and it simply means that the corresponding polynomial will be invariant if you multiply variable y by I. So this is a trivial algebraic identity. So you see that a enumerator polynomial is a convenient mathematical vehicle to store information about the code. So that's enough about codes. Next important thing about them is that we can use a code to define a lattice. I will explain on the next slide how to do it. Also, the formula is given here. So first of all, you define a lattice of integer with a cubic lattice of size 1. It's a lattice of vectors with all coordinates being integer. And then you say that your vector belongs to a lattice associated with the code. If you take x and calculate x mod 2, it becomes a binary string. And if this string, this is a typo, this should be not complex numbers, that should be code. If this string of coordinates mod 2, which is, if it belongs to the code, it means that your vector belongs to a lattice associated with the code. Maybe I should explain how it works. So let's say this is my origin, and this is unit cube. In this case, my unit cube is 2-dimensional. So this is my origin. This belongs to a code. And let's add, let's say, another point which belongs to a code. Let it be this point. In this case, my words, this one and this one. Okay. How do I, so this is just a code. How do I produce a lattice starting from this? Very simply, I take each highlighted point and will transform in all possible directions with a step 2. I move it with a step 2 in all directions. I move it with a in all directions. And of course, in these directions as well, and these directions as well. And once I move it in this direction, I move it to this direction and this direction as well. So in this, excuse me, that was a mistake. So here I will have a quadratic lattice with a size 2. That's the image of, and then this point will also give me a lot of additional points with a step 2. And basically with this code. So this lattice is a lattice associated with this code. Now, this is a completely universal. Something is wrong, probably like this. This is a completely universal procedure. If I started not from this, if I started not, but from this, I also will be able to move it in a parallel way. So it doesn't matter what kind of pattern you have in a unit cube, you can move it in parallel in all possible ways, left, right, and all possible directions with a step 2. After you do that, for some special reason, you rescale things by square root of 2. So I'm trying to do it on my iPad. I can rescale by certain factor, and then you get a lattice associated with a given code. Mathematically, it's given by this formula. You take a vector with integer variables, you calculate x mod 2. If it belongs to the lattice, you rescale it by 2, and that's the point of your lattice. Why this is important? Because, well, first of all, lattices appear in physics. And second, if you want to calculate a theta series of a lattice, and a theta series of a lattice is defined as a sum over all lattice vectors with the exponent I tau x squared, where x is a lattice vector and x squared just Euclidean norm. Apparently, if your lattice is associated with a code, you can calculate this theta series explicitly and express it in terms of a numerator polynomial, where instead of 2 auxiliary variables x and y, you write 2 Jacobi functions theta 3 and theta 2. So this formula is pretty important. It tells you that a lattice comes from a code, then you can easily calculate a theta series of that lattice. Any questions at this point? So at this point, we are ready to connect codes to CFTs. If we have a lattice of a special kind, we know that we can define a CFT. So if we take a code which is self-dual and double even as a code, and we define the lattice the way I explained on the previous slide, resulting lattice will be even self-dual Euclidean lattice in dimension Rn. Those kind of lattices can be used to define chiral CFTs. And then you can easily calculate partition function of that chiral CFT. And essentially, it's a theta series of a corresponding lattice divided by Dedekind eta function. And we already saw on a previous slide that theta function can be calculated, theta function of a lattice can be calculated in terms of a numerator polynomial. So basically, in this case, if you start with a special code, define a special lattice, and then define a special CFT, you can immediately obtain partition function of that CFT just in terms of the code, or more specifically in terms of the spectrum of the code or a numerator polynomial. Okay, any questions? All right, so modular invariant. In this case, actually, it will be modular covariant. There will be anomaly. Well, this construction can only exist if n is divisible by 8. There will be anomaly unless n is divisible by 24. That's because of this denominator, because Dedekind eta function is not behaving well under conventional shift. Tau goes into tau plus 1. It behaves well only if n is divisible by 24. But let's forget about this for a second. This is coming from the denominator. When it comes to numerator, a numerator behaves correctly as it should be to ensure modular invariance. And modular invariance includes 2 transformations. We know that to check for modular invariance, you need to check correct transformation under tau goes into tau plus 1 and tau goes into minus 1 over tau. There are two transformations. You need to make sure that both are taken care of. And if you have partition function given by this formula, modular invariance will be guaranteed, well, modulo this issue with the anomaly, but it will be guaranteed by two algebraic identities. This transformation will be taken care of by this algebraic identity, and this transformation will be taken care of by this identity. This is Mach-Williams identity the code, and this identity comes from the fact that the code was double even. So the punchline is that modular transformation, modular invariance of partition function, we usually think about it as some very complicated mathematical property. Sometimes magic to prove it is very difficult. Well, usually it's very difficult. But in this particular case where you connect your CFT to a code, everything boils down to very simple algebraic. Already see at the Okay, so this is basically the end of my introduction. There's nothing new or original in this part which I said. This connection between classical codes and chiral theories has been for probably 30 years. I should have cited, actually. It's my omission that I did not cite. There's a wonderful paper by Dolan and Osborne discussing all that, and there's other literature beyond that paper. And this is not a very well-known story, but that's certainly well-established and old story, which goes back to. Okay, so the new part is about quantum codes. I want to very quick. So I will be discussing special kind of codes, which are called stabilized. Consider n qubits. So I have n, and the code is a linear subspace in the Hilbert space of your physical system. You have n qubits, so you have Hilbert space of dimension 2 to the n, and the code subspace consists of all vectors psi, which are invariant under action of some abelian group. You have some abelian group, it acts on this code subspace trivially. So from the mathematical point of view, for the code subspace, this abelian group is a stabilizer. And that's why the codes are called stabilizer codes. So can you still see my screen? Because I had some.
Yes, but
okay.
I think we might have missed the an update.
An update.
Well, I don't know. Try writing something.
Yes, I cannot.
It looks like your screen disappeared.
Something has happened. Maybe I will try to connect my my screen again. Okay. It says connecting, but it doesn't seem to be connecting. Let me try one more time.
Oh yeah, I've also had this issue. Sometimes it helps to leave the meeting and come back.
Yeah, I left the meeting on my iPad, and I'm trying to reconnect with my iPad. What I can try to do, just to keep the presentation going, I can use my screen, then I will not be able to write. Okay, let me try. Yeah, I cannot fix that for now. Let me try to show the, yeah, maybe I can continue in this mode. And if my iPad connects later on, I'll try to switch back. Can you allow me to share my iPad, please?
I think it looks like you're connected again with the iPad.
Yes. So
I'll make it co-host, but you should be able to share already.
Yep. Okay. Sorry about this. So you should be able to see my screen now. Can you?
I can't see it.
No.
It says that I'm sharing.
Yeah, but we don't see it.
You don't see it.
Yeah, I think it's safer to just use the slides.
Okay. Oh,
Oh,
We see
it's
something.
probably, yeah, there's probably
now we see
significant
the
lag.
flash. Maybe try writing.
Yeah, somebody is asking to put slides in the chat.
No, you don't need to do that.
I can do it. I just don't know how to actually do it.
Oh, but we have
No
you can
bother.
share the slides.
Hmm?
So,
Okay, so you can see. Okay, so let me try to continue. If it breaks down again, I'll try to switch to the screen. So the idea was that you have n qubits, and a code subspace is a linear subspace in the Hilbert space of n qubits, and you have an abelian group, which is called the stabilizer because subspace invariant. And in this game of stabilizer codes, you choose the generators of the abelian group in the following form. These are Pauli matrices acting on each qubit. So there are 4 Pauli matrices, X, Y, Z, and identity. And obviously, if you take 2 generators of this form, where you have tensor product of Pauli matrices, and you multiply them by each other, there is element of the abelian group also would be a product of Pauli matrices. So instead of writing elements of the stabilizer group in this form, you can simply encode them by the vector C, where each element of the vector C can take 4 values, if you wish, identity, X, Y, and Z. But those 4 values, it is convenient to write them in terms of elements of field F4. And there are 4 elements, and I have written only 3 of them, 0, 1, and then 2 other elements. Basically, these are 3 roots of degree 3 of unity, right? You have 1 and then whatever by 3 and 2 pi and minus 2 pi divided by 3. So you have 0 and 1 and this number and this number. So there are 4 values. And apparently this is the correct structure to encode multiplication of Pauli matrices among themselves. And then you will have an additive code. So you'll have vector C1, which consists of n elements, and each element is one of those 4. And then if you want to multiply G1 by G2, same as take C1 and add it to C2 and use algebra associated with this field F4. Obviously, I'm not leaving you time to comprehend that in detail. This is the case, but let's.
sorry, Anatoly, I'm a bit confused. So the stabilizer code is composed of elements in the Hilbert space or group elements?
Well, it's a bit of a semantic thing. If you're trying to do quantum information and quantum error correction, then the quantum code is a code subspace inside the Hilbert space, which consists of all vectors psi which satisfy this equation. If you're more mathematically inclined, then everything about this construction is encoded in the structure of the abelian group, which we call the stabilizer group. And then this abelian group is mathematically equivalent as a vector space. It's a vector space in this with the elements in F4, and it should be understood as a vector space over the field F2. So you can only add it with multiplying by 0.
But the Hilbert space is a complex linear subspace. So
yes, the Hilbert space is a complex linear subspace, yes.
So one object seems continuous and the other seems discrete. In what sense are they equivalent?
Well, they're equivalent in the following sense. All vectors psi, which are invariant of GI, where GI is given by this formula. All vectors psi are uniquely encoded by this vector C. Well, not this vector C, but a collection of all vectors C in your abelian group. So if you wish, a code subspace is a subspace defined by some projector. And the projector, you don't consider all possible projectors. You only consider some finite number of projectors, and you parameterize those projectors by some vector spaces or finite field. Is that?
Yeah, okay. Thank you.
Okay. So in a more mathematical literature, when people speak about quantum codes, they simply speak about abelian groups, and those abelian groups are vector spaces over field F2 with the values in F4, and this is a definition of quantum code. If you speak to a physicist, for a physicist, the quantum code is a linear space of those psi's, but you can reconstruct one from another. Okay, so I will be more mathematical. So for me, quantum code will be a finite dimensional vector space of that form. And you can also define a numerator polynomial, which will encode spectrum. And spectrum, in this case, it's less convenient to visualize what spectrum is. But basically, instead of keeping the information about the length of the vector, you simply have a vector which consists of different letters. The letter could be 0, 1, omega, and omega bar. And you simply count for each vector how many zeros it has, how many ones, how many omegas, how many omega bars. And that information is called the spectrum. And that information is encoded in the enumerator polynomial. And then you still can define codes, and self-dual codes will satisfy this algebraic identity, which is called McWilliams identity. And then you can also define a real code. And a real code means that all of these generators as matrices will be real valued. And to demand that they're real valued, the only matrix which is complex in the Pauli algebra is sigma y. So to have real valued matrix, you need to say that there are 2 or even number of sigma y's. And for that reason, the number of sigma y's should be even. And then there is the simple identity, which literally tells you that the number of sigma y's in every generator is even. So you have these 2 identities. And of course, you can recognize why you have those 2 identities, because at the next slide, maybe I'll skip the slide. Well, okay, let's remember that we have quantum codes of particular kind, and those codes, their enumerator polynomial satisfies 2 identities. And at this point, I want to connect quantum codes to particular CFTs, which are Narain CFTs. And I have a slide reminding you what Narain CFTs are. Okay. So Narain CFTs are basically compactification of n free fields on a torus, and then also you can have a B field. First of all, you have n free fields living on a torus. Gij is it's a constant matrix which specifies geometry of the torus, and then also you have the B field. So basically, your Narain theory is specified by 2 matrices, Gij, which is symmetric, and Bij, which is antisymmetric. Those Narain theories are uniquely identified by Narain. Starting from this description, you can have a Narain lattice. Narain lattice is even self-dual lattice in Lorentzian space with a signature n, n. And then for the Narain lattice, you can define the CFT partition function, which is simply theta function of a lattice divided by Dedekind theta function to the power 2n, but here you have a modulus. So there is no problem with the anomaly. For any n, doesn't have to be divisible by 8, doesn't have to be divisible by 24. For any n, you have modular invariant partition function. So this was sort of a very quick reminder what Narain theories are. And the key point of what we did with Al Shapir about a year ago was the connection between quantum codes and Narain lattices. I'm not giving you the construction. It's actually very, very simple. And basically it goes like that. F4 includes 4 elements, but instead of writing them like that, you can write them as pairs of binary numbers. So this guy will be 0 will be this one, 1 will be this one, omega will be this one, and omega bar will be this one. And once you have 4 elements shown as a pair of binary numbers, basically you can map your quantum code to a classical code of double size. And from there, you can use the procedure which I explained before and map it to a lattice with the signature n, n. And we have shown that if you start with a quantum code with particular properties, the resulting lattice will be Narain lattice. And then, of course, the punchline here is that this partition function can be given in a very simple way by a numerator polynomial of a quantum code. And as you can already guess, modular invariance, which is an invariance under 2 transformations, is guaranteed if your enumerator polynomial satisfies those 2 identities, which I have highlighted 2 slides ago. So this is basically the main idea behind our work, or the main point of our construction. Quantum codes. And modular invariance reduces to some algebraic properties of some polynomial, exactly how it was for the classical codes.
What's the role of the Narain moduli space?
Well, we cannot have Narain CFT map to codes. So we have quantum codes of a particular kind, so a family of quantum codes. We can map them to a subfamily of Narain theories, which we call code theories. But of course, those code theories, first of all, there is finite number of them, because for any dimension n, there is finite number of codes. So there is finite number of theories, and it's a discrete set. Narain theories form a continuous manifold. So in that manifold, we pick certain points in some specific way. We cannot generalize.
Is there some way of characterizing, what nice property should those things satisfy? Like some big gap in the spectrum, or?
No, they don't have big gap in the spectrum. Rather, they should have small gap in the spectrum. These are rational. This is some family of rational CFTs. Not all rational CFTs can be described this way, but of course we do not know if our construction, well, we kind of know that our construction is not unique. So there are probably generalizations. If you're super optimistic, you might hope that, I don't know, all rational Narain CFTs can be related to codes. I think your question should be boiled down to the following question, which is one of the conclusions I have. We do not really know what the physical meaning of codes in the context of CFTs. Once we understand that, we will be able to understand how to generalize that, let's say, to all Narain theories. Schematically, I think if you want to describe non-rational CFT, then your code space or your number of qubits should be infinite. But that's perhaps the only intuition I have at this point.
But at the moment, basically you're saying that the arrow goes one way. That is, you hand me code, yes, and I'll hand you an Narain CFT.
Yes, of course. But that's exactly the same what happens with classical codes and even self-dual lattices in Euclidean space. Any double even self-dual code can be mapped to a lattice, but not all lattices have code pre-images, if you wish. Right?
Okay.
So we cannot do better than that in a sense. Okay.
Can I ask you, so the construction that you gave here has at least in the code level, has a natural generalization where you replace the qubit by a dimension k representation of SU2?
Well, a qubit, yes, of course.
Yeah. What happens in the CFT when you do that?
Right. So this is not known. This is something I'm currently working on with Nick, my graduate student. I saw him in the audience in the beginning of the talk. He's likely still around. We don't know the full answer yet. The conjecture is that, so let me maybe describe those code CFTs from the point of, as Narain theories, what they are as Narain theories. Apparently you can use T-duality. Let me finish the slide, and while finishing the slide, I will be answering your question as well. If you speak about quantum codes, there is a natural automorphism group, which is related to possible choices of different bases in the Hilbert space of qubits. So I probably don't have time to explain that in detail, but the idea, but this is a very well-known thing in the context of quantum codes. If you do quantum information, quantum computation, you have different bases for your qubits, and therefore different codes are mathematically equivalent. The question is, what is the counterpart of that? And from the point of view of F4, you have 0, you have 1, and you have these 3 points on each angle. And of course, you can rotate by the angle 2 pi over 3, and that should be some mathematical symmetry of the code, which takes one code and produces an equivalent one. So this is a code equivalence. Some part of this code equivalence group becomes T-duality. So this we know, this we established in this paper with Al Shapiro. And this is a beautiful story, because apparently if you start playing with T-duality, you can the code or T-duality or automorphism to what is called the graph code. The graph is not something we invented, unfortunately. It was invented 20 years ago in the context of code theory. And the idea is that any code using equivalences can be presented in this form, and it will be parameterized by some symmetric matrix Bij, which is an adjacency matrix of a graph. So you can parameterize all stabilizer codes by graphs. And on a CFT side, you can use T-duality and always bring your compactification. So remember that your compactification is specified by the metric and B field. So apparently by using T-duality, any code theory can be always brought to compactification on a unit cube. Well, it's not unit, it's a square root of 2, but it doesn't matter, to a unit cube. And all non-trivial information will be sitting in the antisymmetric B field. And this B field, for your theory to be rational, for your theory to be related to quantum codes, this B field has to be an antisymmetric matrix which consists of entries 0 or plus minus 1. And because of additional T-dualities, apparently this B field has exactly the same amount of information as the adjacency matrix of a code or adjacency matrix of a graph. So basically, all the code theories, all the Narain theories, they are parameterized by a cube. You compactify on a cube. You have non-trivial B field, and this B field can be encoded by a graph. And you can ask, that doesn't kill all the symmetries. There is still additional symmetries, additional T-dualities, and you can ask how those T-dualities act on a graph, and they act on a graph in a rather non-trivial way. There is this edge local complementation. That's a special operation which takes a graph. I'm not explaining for the sake of time. You take a graph and you use this operation and you produce another graph. And for those two graphs, if you go back and produce adjacency matrix, and then from there you take the B field and consider two CFTs, those two CFTs will be T-dual. So there is, perhaps I was going too fast through this and it's difficult to follow the details, but the idea is that there is a natural notion of equivalence at the level of codes. And this equivalence becomes T-duality at the level of CFTs. Now, going back to Clay's question, if you have non-binary codes with qubits, I have a conjecture, which we're trying to check, that then you need to compactify on a cube of size square root of P, where P is a dimension of your local Hilbert space. That's whatever your qubit. Okay, and then of course you have B field, and B field some properly quantized B field will encode information about quantum code. That is a potential answer. We do not yet know if this is correct. Did I answer your question? Okay, let me move forward. Yeah, okay. Let me move forward and give you some interesting results. So basically, the part of the story which I went very quickly through was that these code Narain theories can be parameterized by graphs. And that goes in with graph codes in the quantum information theory. And then you can classify all graphs with respect to T-duality equivalence. This is T-duality. And after you do that, you will find interesting examples when your codes or your code CFTs are not T-dual, but they have the same spectrum. And the first example like that happens for n equals 7. Here you have two graphs. Both of them have n equals 7. It's a highly non-trivial thing, but I want to assure you that those graphs are not T-dual to each other. But quite surprisingly, they have exactly the same enumerator polynomials. And since they have exactly the same enumerator polynomials, we actually have an example of isospectral theories. And if you're familiar with the story, this is a non-chiral analog of Milner's example. Milner's example of n equals 16 even self-dual lattices. One of them is E8 plus E8, and another is what is called D16 plus. Those two lattices are associated with two different codes, like in our case, they're not equivalent to each other. Same enumerator polynomial, which means that as a CFT, if you wish, spectrum of those CFTs are the same. Okay, and that was a unique example, which it answered the question if you could hear the shape of a drum. The answer is that you cannot hear the shape of a drums with the same. A non-chiral analog of that, it already appears for n equals 7, which means that we are talking about Narain lattices in R7,7 space. This is a unique example in n equals 7 we know. For n equal 8, we already have over 60 new examples. So the number of those isospectral theories grows very, very rapidly. And by connecting them to codes and enumerating codes, which is an algebraic thing, it's much simpler to enumerate in Narain theories, we can produce a lot of those isospectral examples. So this is one first application of this connection between codes and CFTs.
Toya, what's the analog of D for this quantum code? Is there a D, this distance function?
For the quantum code, there are several different D. So first of all, there could be D, which is simply number of non-zero elements. So basically, you don't care whether you have an omega bar, you count all of them together. So this is what is relevant to quantum computing. Quantity, which we call D binary, and is basically it's a number of omegas plus number of omega bars plus 2 number of ones, and they enter in a non because this quantity is closely related to spectral gap in a Narain theory. So in the Narain theory, as a physical theory, spectral gap is more related to this binary distance. So you have two different characteristics which are relevant.
And the D non-binary, does that have a meaning in the CFT?
No direct meaning, no. No direct meaning. At least within our construction, no. Okay, next thing which we can use is the fact that to produce modular invariant Z, we don't really need to start with the code. We can simplify the construction, and we can say that we have W, which depends on 4 variables, if you wish, and this W satisfies certain algebraic identity, plus also coefficients should be integer and positive. And to generate such omega, this is a very straightforward problem of linear programming. So you can write a simple program which will generate a lot of those W's, and each W can be used together with this formula to produce modular invariant Z, which satisfies all the properties of a partition function of a CFT, but there is no obvious CFT counterpart. So we call such W and we call such Z fake, because they may not correspond to any CFT at all. We do not know if there is a CFT.
Well, just to clarify, W is a polynomial, right?
W is a polynomial.
What's its degree?
It's a homogeneous polynomial of degree n, where n is the dimension of the space.
Ah, okay, thank you.
Yeah, and there is some theory that this polynomial should actually be a polynomial, polynomials which are known. So if you want to write a program, it's actually very simple to do it, because invariants under those two identities are taken care of, because this is an arbitrary polynomial of 3 specified polynomials. So the only thing you need to take care of is that coefficients in terms of this x, y, and z are positive and integer. And these are exactly the things which you can do with linear programming. Okay, so second application is that we can generate a lot of fake partition functions. And all of those partition functions are solutions to modular bootstrap, yet we do not know if they correspond to any theory. That's an option, and likely any theory at all. And the conceptual takeaway here is that you have this problem of model, which you try to solve in the space of all CFTs, or perhaps you can try to solve it in the space of Narain CFTs. And usually what you try to do is to find consistent solutions, or find consistent solutions which optimize spectral gap or something like that. And of course, this is difficult to do. There is a whole modular bootstrap program. You can use a convenient ansatz which comes from codes. So basically, you're not considering Narain theories, you can consider a subfamily of Narain theories. And within that subfamily, your constraints reduce to some algebraic constraint level of polynomial. And then instead of doing very complicated linear programming or semi-definite programming at this, you can do linear programming at the level of, and level of a numerator polynomial is not invented or physicists invented. Mathematicians have been playing in the context of codes for many decades. So basically, this is a connection between modular bootstrap and some activity which mathematicians have already excelled a long time ago. Okay, so this is some preliminary conclusions. Is the following. We have different objects. We have CFTs, we have lattices, and lattices are closely related to the problem of sphere packing. If you have a lattice, for each vector of a lattice, you can put a sphere of a maximal size and you will produce a sphere packing. And also you have quantum codes. Well, you can have classical codes, but let's have quantum codes. And then all those 3 things go in parallel. For example, if we start with very special quantum codes, we will have special Narain lattices, and then we'll have Narain CFTs. And then certain properties of those CFTs, like spectral gap, they would correspond at the level of lattices and sphere packing, it will correspond to packing density. And at the level of codes, they will correspond to binary distance. This correspondence is a little bit, it's more like a moral correspondence, because literally to have spectral gap, let me erase this and just say that for the binary distance to literally control spectral gap, work for sufficiently small n. When n becomes large, spectral gap is not controlled by binary distance. Moral counterpart of spectral gap. And I probably don't have, maybe after the talk, if you ask this question, I will explain why this happens, but the same problem happens already at the level of classical codes. But the important part of the story is that we have this modular bootstrap program, and then there is a connection between modular bootstrap and linear programming. For example, the famous work by Hartman, Mazak, and Rostelli in 2019 have demonstrated that modular bootstrap reduced to the level of spinningless bootstrap. So if you consider, but don't write all possible constraints, only write constraints which comes from what is called a spinningless bootstrap. Those constraints become equivalent constraints of sphere packing introduced by Elkis and Cohen. And our story basically goes in parallel. Our linear, well, so this is the work by Hartman, Mazak, and Rostelli, and our work goes like that. We are basically saying that modular bootstrap reduced to some other ansatz reduces to the linear programming at the level of codes. So this is I think, conceptually important takeaway, so let me repeat it. If you start with the modular bootstrap, which is immensely, and reduce it somewhat in a special way, you get the linear programming formulation, which people already saw in the context of sphere packing. We play a similar game. You start with the modular bootstrap, you reduce it to even smaller ansatz, even more restrictive ansatz, and you uncover linear programming at the level of codes. So this problem people worked on before in the context of sphere packing. This problem people worked on before in the context of codes. And the point is that both problems embed, as some particular cases, in the modular bootstrap program. Okay. So I have a slide about generalizations and extensions. I'm kind of running out of my hour, right? I don't know, how much time do I have?
You can take still 5 minutes
Okay.
or so.
So let me try to go through 2 next slides. So there are a lot of questions remain, and a lot of obvious questions and less obvious questions. There are a number of projects I'm involved right now, and maybe I'll just tell you what are the questions I'm working on. So one obvious question, we have a lot of fake partition functions associated with the central charge 3 and 4. We just generate them with linear programming. These are very, very particular polynomials, W, which you can easily work into fake partition functions. We do not know if they are truly fake or not. At this point, we are trying to understand if those partition functions might or might not come from Narain theories, which are different from code theories, right? So hypothetically, well, we know for sure that there is no code theory because there is no code. These are W's not associated with any code. But it still could be that there is some Narain theory not coming from our construction, some new Narain theory, which produces exactly this Z. So this is already a very difficult problem to show that there is no Narain theory which gives you this particular Z. But I'm optimistic that we will be able to work it out. And the next step would be to understand if there are perhaps other non-chiral CFTs with central charge 3 or central charge 4, which can give you or may not give you this particular partition function. This is one direction. Another direction is that we calculated torus partition function of a CFT, reducing it to a spectrum of a code or a numerator polynomial of a code. You can ask what happens if you compactify your if your CFT is living not on a torus but on genius 2 surface or genius G surface. There is a hope that in this case a code CFT, a partition function of a code CFT, also can be calculated just in terms of a code. I contributed next to nothing to this consideration. This is all due to my student Ashish Kakar and his collaborators. But basically the idea is that, let's say for genus 2, you need to generalize a numerator polynomial. A numerator polynomial, you have a sum over code words. For genus 2, you need to sum over pairs of a code word. And besides lengths of the code word, you also need to keep information about relative angle. So that's kind of geometrically natural. You sum over pairs of the code word, and then you keep information about the angle. I suppose if you want to have genius 3, then you need to sum over triples of the code word and maybe some relative angles in these triples of the code words. Then, as I mentioned with another graduate student of mine, Nick, we are trying to generalize the construction for non-binary codes. But then a very important question, which I should ask myself or otherwise me, is whether this construction I presented has deeper meaning, if there is some physical meaning behind connection to codes, maybe in the context of correspondence or some quantum information. I should mention there was a paper by Harvey and Moore about a year ago where they connected quantum codes to vertex operator algebra. It's a complementary proposal. We looked into this proposal, in our case, it doesn't work. Also, it might be that there is a generalization which would be sort of in between their proposal and ours. This is something I don't understand. But the question remains about holographic interpretation and the physical meaning. So maybe I will spend a minute trying to sketch some idea. If you have a CFT, a Narain CFT on the boundary, you can think of a holographic description in terms of Chern-Simons, right? And you can make it very, very explicit. And if you have Chern-Simons, you know that in principle, Chern-Simons, if you take the chiral part of Chern-Simons, the wave functions of Chern-Simons on a handle body, so this thermal ADS, thermal ADS will form a handle body. Wave function of a chiral Chern-Simons on a handle body, they form finite dimensional Hilbert space. This is a case of conformal block of the corresponding CFT. So this Hilbert space is finite dimensional, which begs some relation to Hilbert space of qubits of those qubits for which quantum codes work, if you wish. So this is a very natural idea. As soon as you have finite dimensional Hilbert space, you want to make connection with these quantum codes and qubits. But I have to say that this idea did not work in a simple way. It did not work in a simple way. I started discussing that with Matt Boykan and his graduate student. And right now we have some proposal, but it's not finished and it's very it's rather complicated. And it says that this picture with the conformal blocks of the corresponding CFT, it might be related to automorphism, this C-duality, it's automorphism of the code equivalence group. So I probably don't want to go into details here because it's very, very technical. And also it seems to me that it doesn't answer my initial question. It might show that there is some relation between finite dimensional space of conformal blocks and quantum code, but I still feel like the main question remains open. What is the holographic interpretation of these quantum codes? So I will just leave this question as open, maybe just mention that there is some work in progress. I have 2 more slides. Is it okay to go through them?
Yes, go for it.
Okay, so this was an extension of what we did with Al Shapiro a year ago. But apparently this construction, mapping quantum codes to Narain theories, we are almost done, Adar Sharon, working on a new construction. Apparently, you can start with another family of quantum codes. In the previous part of my talk, I was working with a special family of quantum codes, which are called real and self-dual. Apparently, there's another family of codes which are isodual in a special way, and there are some additional properties being satisfied. And if you start with codes of that kind, you can also map them to the subfamily of Narain CFTs, but this will be different subfamily of Narain CFTs. And this would be a different mapping. And among the code CFTs which you obtain this way, there will be theories which in dimension, which in dimension 6 and 7, they maximize the spectral gap. So the story of maximizing the spectral gap for the given central charge, it goes in parallel with the story of trying to maximize density of sphere packing. And remind you that there is the story of sphere packing, and there are special dimensions, namely 3, 8, and 24, for which optimal sphere packing is achieved at the level of a lattice sphere packing. And for the dimensions 8 and 24, these lattices are special lattices which are important for physics. One of them is E8 and another is Li. And those are also related to codes. So in those two special dimensions, 8 and 24, maximal sphere packing is achieved by lattices which are related to codes. Something similar is happening with the question of spectral gap for Narain CFTs. In the dimensions of 6 and 7, we could find Narain lattices which are related to two special codes. One of them is the hexacode, and another is an unknown code, meaning I can write it explicitly, but it has no proper name. It's an isodual code of this kind. And those two lattices, those two codes give rise to two lattices. And we know they're optimal. Optimal means that they achieve maximal spectral gap, because those results match numerical analysis of Nima and friends. Okay, so basically the punchline is that similar to the case of sphere packing, where codes sometimes give you the optimal solution with the maximal density, also of these codes in particular dimensions give you optimal theories. There is a very good and very simple argument which tells you that as you increase dimensions, your codes will not be helpful. You need to invent new constructions to go into higher dimensions. But for small dimensions, codes are very good vehicles to produce theories with a maximal central charge. Okay, so this is some upcoming work. Let me conclude. So in a nutshell, we started with quantum codes and produce an explicit construction how quantum codes with a subfamily of Narain theories, and that we saw toward the end of this talk on the previous slide that there is actually more than one construction. And therefore, all those important questions about physical and underlying meaning, connection to holography, they become even more complicated because there is no one construction. It might be that one construction would be canonical, another construction are accidental. I do not know. Or it might be that all constructions are physically meaningful and there are different, there are different relations to holography. Another important non-technical punchline is that relation between codes or Narain lattices is qualitatively the same as the relation between classical codes and sphere packing. In small dimensions, certain very special codes maximize density of sphere packing, and the same is here. In certain dimensions, certain codes give rise to Narain theories with maximal. You can ask if there are special codes which give rise to theories with another special properties. For example, the famous Leech lattice gives rise to a monster CFT, a very, very special CFT with the largest discrete symmetry possible. And algebraically, it's very special because the symmetry of that CFT goes beyond geometrical symmetry of the lattice. The question is, do we have non-chiral counterpart of that story? That's a great question. Of course, we don't have it yet. Otherwise, I would certainly tell you that about that example, but it's that such an example may exist. But in general, I think the relation between quantum codes and non-chiral Narain CFTs is qualitatively the same as relation between classical codes, sphere packing, and chiral CFTs. And then more tangible conclusion, more tangible result is that we generated a lot of modular invariant fake Z's. Basically, we have found many solutions of conformal bootstrap equations without knowing what kind of theories they describe. And we conjecture that actually those solutions of modular bootstrap has no CFT counterpart, which actually is an interesting takeaway for your modular bootstrap program. Of course, you know that modular bootstrap is a set of necessary conditions, but not sufficient. But now we can give you many examples where we likely have a solution which has no CFT counterpart. And also, as another very concrete result, we have many examples of isospectral theories. In the chiral case, there was this Milner's example, but otherwise, there are not so many examples of isospectral theories or isospectral lattices people know. In the non-chiral case, we generated dozens and dozens, and actually, if you're willing to go to n equal 9 and 10, there will be thousands of those examples. Okay, so these are the conclusions I have at this point. I will have to wrap up here because I already went over time, but basically this is only first part of my talk. My talk was intended to be consistent of two parts. First part was about using codes to study properties of very special theories with a maximal spectral gap or somehow special. There was another part using codes as an ensemble. So I don't have time to tell you any technical detail of that, but maybe just to provoke a discussion, I'll jump to conclusions, which also include conclusions about this ensemble story. I will wait a second before the screen updates.
Wait, why do you say these fake partition functions don't correspond to a CFT? What's wrong with them?
Right, so if you have a code, you can always define W, but sometimes you can have W which satisfies all algebraic identities you need and all other properties, and the coefficients are integer and positive, but there is no code. Those W we call fake. And since there is no code, there is no obvious CFT, you can put as a counterpart for the corresponding, this W you can use to produce Z, but there is no CFT. At least there is no natural CFT which you can be sure corresponds to the Z.
But you can produce a set of degeneracies and scaling dimensions that is consistent.
Yes. This Z satisfies modular bootstrap equations. You can deduce dimensions and degeneracies and the spin, everything, but you do not know if there is CFT which gives rise to the spectrum. Okay, so just basically, I want to end with this conclusion slide because this conclusion slide says that there is a part of the story which I didn't have a chance to speak about, and the part of the story which we discuss is that codes can be used to study special theories, but also codes can be used to study ensembles of theories. And that's a valid application, and basically codes provide new toy model or new playground to study ensembles. And these are always finite ensembles, and you can usually calculate things pretty explicitly. For example, this calculation of density of states, we have shown that the variance is exponentially small. We could do it easily because we considered codes as a toy model. So I have to conclude. I feel I went over time. I hope you will ask questions and I will have a chance to maybe explain some things in more detail. Thank you.
All right, let's thank Tulya for the nice talk. And maybe we can take one question now and discuss more during the discussion session.
Just to clarify then, when you say there is no known CFT, I mean, what does it mean to have a known CFT anyways? It's like, yeah, in some cases you have some free field construction, in other cases, you know, you can play tricks with boson dilation. So I guess the degeneracies and the spectrum aren't enough to fix a CFT, but if in addition to that, you had the OPE coefficients, I would say that is the definition of a CFT anyways.
I would agree that this is a definition of CFT, but we do not have OPE coefficients. I'm saying that I have Z, which is modular invariant, but you do not know if you can complete it by OPE coefficients such that it would define a self-consistent CFT. If you wish, this is essentially the question.
Yeah.
When I say that there are no known CFT, it means that there is no CFT which would give you this Z, and there might be no such CFT at all. And it is a possibility that it's impossible to start with a Z, meaning to start with this spectrum and try to complete it with OPE coefficients, and it might be impossible to complete it with the OPE coefficients.